Here we go with our lecture on torque on a current carrying loop in a uniform magnetic field, which is the basis for all electric motors, right? This is how any electric motor works from a fan, think of a fan in your bedroom at night, or well, all electric motors. Okay, so the objectives we're looking at here today are D.2.B and C. So let me just pull that up real quick before we get started and see what those are. So students should understand the force exerted on a current carrying wire in a magnetic field so you can indicate the direction of the magnetic forces on a current carrying loop of wire and determine how the loop will tend to rotate, right? Torque is rotational force, right, basically. And also the magnitude and direction of the torque experienced by a rectangular loop of wire in a magnetic field. So switch back to the paper. Okay. So first we're going to consider a rectangular loop of wire with a current flowing through it, current I, and it's in a uniform magnetic field B. And the first thing we want to figure out is what is the magnetic force on each side of this loop. And remember, we learned in the last lecture how we would find the force on a straight length of wire, right? And that was basically we got it from the force on a moving charged particle, and then looked at all the moving charged particles in a wire, and we found that the force was equal to the current times the cross product of the length of the wire with the magnetic field. So we can try this out for each of the four sides of our loop. And then once we do that, we'll be in a good position to figure out the torque. So what we've got, here's our loop. I've drawn a little coordinate system here because we've got two views. This is looking at it from the front, right? So x-axis, y-axis. We've got a magnetic field in the negative y direction. And then the current is flowing around, here's I, right? The current is flowing around this loop in a clockwise direction. The length of this top side here is lowercase a. The length of the long side here is lowercase b. And when we look at torque, we'll be looking at how it's going to rotate about this axis here through the center. All right. This is a side view of our loop of wire. And in this view, the z-axis is over here to the right. Right, the y-axis is the same, and then the positive x-axis would be into the page, the way we're looking at it here. So I think we have enough information that we can figure out the force on each side. So let's look at the sides first. Right, so the force on the left side here. And in order to do this, remember, maybe it'll be, well, let's see, can anybody tell me what the magnetic force is going to be on this side here? We know the current is flowing in the positive y direction up here, and the magnetic field is in the negative y direction. Does that tell us what the magnetic force is going to be on just this left side of the loop here?
You mean the direction of the magnetic force?
Yeah, we can talk about the direction or the magnitude, really.
So wouldn't it be moving to the right?
Well, let's see. Hold on. Let me rewrite this as well. So for the magnitude of this force, the magnitude of the magnetic force, remember, is going to be the current times L times B times the sine of the angle, right? And the sine of this angle is the angle between L and B, right? The length of the wire and the magnetic field. So in the case of the side here, what is that angle going to be? If we've got the length of the wire, the
180.
Current, yeah, 180.
Wait, so technically it's going to be going inside or outside the page?
The sine of 180 degrees. We know this. Sine of 180.
I'm terrible at calculus, I'm sorry.
Greg, it's 0, right? Sine of 180 degrees is 0. Just
Oh,
like
yeah. Oops.
0. All right. So the point is that there's on this side of the loop, and actually also on this side, because on this side, the magnetic field is in the same direction as the current. On both of the sides, the magnetic force is 0. All right. And that's because when we're taking a cross product, if the two vectors are parallel or anti-parallel, then that cross product is equal to 0, right? That's sine theta equals 0. When we take a cross product of two vectors, only their perpendicular components contribute.
So there's no magnetic force at all.
There's no magnetic force on this side here or on this side here.
I see.
And that's because the charge is moving parallel or exactly opposite, anti-parallel to the magnetic field. Right? Different story on the top of the bottom. We're not going to get 0 on the top of the bottom. Okay.
Yeah, because it's perpendicular to.
Because it's perpendicular, right? So for the top and the bottom, both of those angles are going to be 90 degrees. So the sine of 90 is just 1.
It doesn't make much sense to have a right-hand rule with your hand being straight.
Right, exactly. That's why you can't do it, right? If I was going to try to, exactly, right? I can't point my fingers in one direction and then curl them in the same direction, right? That doesn't work. Break my fingers. So let's look at the top, this loop here. Right, so we've got, well, we can find the magnitude pretty easily, right? The magnitude is just from this. Right, the current we know is I. What's the length of the wire on the top? That's just this lowercase a. And then the magnetic field strength B. So the magnitude of the magnetic field, the magnitude of the force on this piece of wire is current times A is the length times capital B, the magnetic field strength. Let's figure out the direction. Right? If we've got the current flowing to the right, so the length of the wire to the right, and the magnetic field down, right? So I'm looking at this diagram. If I go right, is the direction of my current crossed with the magnetic field down, my thumb points into the page, right, in the negative Z axis. All right, so the negative Z direction. So it's a little hard to draw the force on this one, right? It's going to be this top of the wire is being pulled into the page. But if I'm looking at the side view, then the force on the top is going to be like this. All right. The way I've drawn it here, right? I'm kind of pulling this loop on its side like that. Do we see that? Why that's in the negative Z direction? Right? My fingers are pointing in the direction of the current, curled in the direction of the magnetic field. So my thumb points into the page there. Are we okay with that? So if we look at the bottom, right, we know both. So we've done 3 of the 4 sides, right? These 2 sides are 0. Top, we've got a negative Z direction force, magnitude IA times the magnetic field. On the bottom, well, the magnitude is going to be the same, isn't it? Because we've got the same current. This length is the same. I guess I drew it kind of crooked, but this length down here is the same as this length up there, lowercase a. And the magnetic field strength, if the field is uniform, is the same there. So the only difference is the direction. Right? So if I want to find the direction of the force on this bottom piece, well, when I get down here, the current is moving to the left. So now I have to start with my fingers curled to the left or pointed to the left. I still curl them in the direction of the magnetic field, which is down. But now that makes my thumb pointing upwards or out of the page, which is the positive Z direction. All right, so since the current is flowing, basically these two legs of the loop are exactly identical except the direction the current's flowing, right? If it's moving to the right up here, it's moving to the left down there. So that means the force is going to be pointing in the other direction. If I draw in the force on the side view, the plus Z direction looks like this. All right, so these two forces are equal in magnitude, but they're opposite in direction. Right, so those magnetic forces balance out. The loop of wire isn't going to translate anywhere, but there is going to be some torque, right? You can kind of see that it's going to make our loop of wire rotate about this axis. Right, if you push the bottom of it to the right and the top of it to the left, it's going to start to rotate like this. Right, and we start to have a magnetic motor or an electric motor. Questions so far about the forces on each side of the loop? Oops. All right, so remember, we used the equation that we found last time, right, which is the magnetic force on any length of straight wire in a magnetic field, uniform field. Right, we found that using the right-hand rule, we found that the sides are 0. There's no force on the sides, and the force on the top and the bottom are equal, but in opposite directions. So looking from the side, we can see that our loop of wire in a magnetic field with a current through it is going to rotate. Okay. So the only other thing now is to figure out what the magnitude of this torque is, right? And that's not much more than we've done. Right, we do have to go back to mechanics to remember that to calculate the torque is R cross F. Right, where F is the force, right? R is just the vector from the arrow, or sorry, the vector from the axis to the point of the force. All right, so there's going to be a torque on this loop about 0.0 from the top force and a torque on 0.0 from the bottom force, and the total torque, then we just add them together. So let's see what we get. So, well, we're also going to see that the magnitude of the torque, since this is a cross product, is just going to be R times F times the sine of the angle between the two.
Mister, so that differential in force between the two plates.
Yeah. Well, they're not plates.
Not plates, sorry.
Two pieces of wire, right?
Two pieces of wire, because they circulate around, like, I'm assuming metallic thing or something.
Mm-hmm.
So that's what, like, creates a force on two different places, and these two opposite places cause it to rotate.
Yeah, you can see, well, you can kind of see, right? If I've got a loop of wire like this, I'm looking at it from the side, right? And I'm going to assume it's going to rotate about this point in the middle. Then yeah, right. If I have this here and I pull to the right on it at the bottom and to the left on it at the top, then it's gonna start to rotate, right?
So
yeah.
I'm guessing this is more into the thing we're going to learn after, but doesn't the magnetic field need to switch whenever it reaches a point? Because here it's just going to rotate and then get stuck at a certain point.
Yeah, so this isn't a very efficient electric motor. You're kind of noticing that, and that's good. Yeah, so you're right, because once it it's going to feel a torque, and which is going to tend to rotate. But when it gets to this point here, then all the
forces, all the current is like parallel to the-
Right. All the current would be parallel to B, and you're not going to have any force at this point. There should be enough, if there's not a lot of friction in your motor, there should be enough speed that it kind of passes through this point and gets to a point where there is a force again. So it should keep rotating, but there are better ways to do it, to either switch the direction of the magnetic field or the current or something like that. No real motor you would build this inefficiently, except to kind of demonstrate that it works.
I see.
But
Thank
you're
you.
right. The farther this rotates away from the vertical, the weaker the torque's going to be.
And it's going to depend on the equation above the angle with sine.
Yep. Yeah. This is going to be important on figuring out once it starts to rotate, right? The torque's not going to stay constant. The force isn't going to stay constant, and it's going to have to do with this angle. Yeah. That's good to notice. But let's see. Let's figure out what we get as far as the value for the torque. Right. So let's see. Looking at the torque on the top piece. Right. The R for the top piece is basically the vector from the axis up to the point of the force, which is up here. So if I do the cross product, so these are perpendicular, right? So the magnitude of the torque is just going to be R. And what's this? What is this different distance in terms of things we've defined? Anybody see that?
So can you repeat the question?
This distance R from the axis here to the top loop, top wire. What is that distance in terms of things that we've defined at the beginning?
It's just A divided by 2.
I
think.
Not A divided by 2, B divided by 2. Right? This isn't necessarily a square. So this side is B, so this vector R is a length of B over 2. So what we get for the magnitude, this R is B over 2, lowercase b, not the magnetic field.
Wait, so sorry, what's A in?
A is this length.
Oh, I
B
see.
is this length.
B the vertical. I see.
Yeah.
For some reason, I thought the horizontal. Or sorry, never mind.
That's okay. So the torque on the top loop is B over 2 times the force, which we know is I times A times B, the magnetic field. And the direction, right? The torque of the direction. Remember, the direction of the torque kind of points in the direction of the axis that it's rotating around. And if I do R cross F, right, I know that R is towards the top of the page here. I know the F on the top loop is into the page, looking at the front view. So the torque axis is to the left. So the negative X direction. Switch to a pencil for some reason. Does that make sense? Why the torque is the torque axis is the negative X direction. Right. R up, F into the page, torque to the left. We can look at the bottom. Right. We can look at the sides as well, but since the force is 0, the torque's going to be 0 as well. But on the bottom, right now, the R vector, the vector from the axis to the point of the force, is this vector. We can see the magnitude of this R vector is still B over 2, right? It's still half the length of the long part of the wire of the loop. So we have B over 2. The force on the bottom was still I times A times B. And the direction, well, this time the R vector is pointing down in the minus Y direction. And the force is in the plus Z direction. So I think I have to go like this. My fingers point downwards. I curl them in the plus Z direction. And then my thumb points again to the left in the minus X. Right? The right hand rule for this one, R cross F, My R is in the minus Y down. My F is in the plus Z, right, for the bottom, plus Z. So my thumb points to the left. The torque axis in the negative X direction again. And it's good that these torques don't cancel out. If the torques canceled out, there would be no rotation. All right, so we can see now what the total torque is by just adding these together. They're in the same direction. So what do I get if I have B over 2 times IAB plus B over 2 times IAB? I just get the
B on its own.
Yeah, the B by itself, right? If first it looks like this. If I do this, what do I can rename this A times B, lowercase a times lowercase b. What quantity is that going to give me? In a rectangle. If I multiply
The area?
Yeah, the area, right? This has the area of the loop in it, right? Lowercase a times lowercase b. A and B are the sides of the rectangle. That's just the area. So the torque, and this actually works whether it's a rectangle or not, is the current. I'll use capital A for the area times the magnetic field. And again, in this case, we have the minus X direction. And that's just the axis, right? That's kind of it rotates about the X axis in the negative direction. All right, so in general, if you have a current carrying loop and a uniform magnetic field, the torque, which is going to make it rotate, is the proportion of the current, the area of the loop, and the magnetic field. And that's the basis for all electric motors. Questions about this? All right, good. So we'll stop there, the lecture there for today.